Welcome back. We've made it to our series finale on mammography physics. Today, we are putting everything together and exploring the absolutely critical skill of artifact troubleshooting. This right here is where all that physics we've been learning smacks right into the real world of daily clinical practice.
You know, this phrase from Dr. Mohammed Jafar just nails it. It perfectly sums up what we're talking about today. Every little glitch or imperfection you see on an image isn't just random noise. Nope, it's a clue, a direct consequence of the physics we've been studying. But there's another layer to this story we really need to dig into.
And that's exactly our job today. We're going to play the role of digital detectives, learning how to spot the false clues, the red herrings that can pop up in a mammogram, clues that, if you're not careful, can lead you way, way down the wrong path.
And believe me, the stakes could not be any higher. An artifact you don't recognize isn't just some small technical glitch. It can have massive consequences. It might hide a real problem, a cancer that gets missed, or it could do the opposite, create a total false alarm, sending a patient for stressful, expensive, and completely unnecessary follow-up tests.
Okay, so where do we even begin? Well, to solve any mystery, you've got to organize the clues, right? As you can see here, all these different artifacts can be neatly sorted based on where they came from. Understanding this is our first and, honestly, our most important step in cracking the case. So step one in any investigation is asking the big question: did this come from the patient or from the machine? We're going to start by looking at artifacts that actually come from the patient, because these can be some of the most common and, frankly, the most convincing imposters out there.
Now check this out. It's kind of scary how similar these two things can look. On the left, you've got simple deodorant specks from tiny metal particles, and on the right, microcalcifications, a potential early sign of cancer. You can immediately see how mistaking one for the other is a really big deal.
In fact, this is such a critical point, such a classic doppelganger, that it's a staple question on the board exams for radiologists in training. It's a fundamental test of their detective skills right from the get-go.
All right, moving on to the machine itself. Let's talk about detector artifacts. Dead pixels are a classic example. Think of them like a clue that's always left at the scene of the crime. It's in the exact same spot on every single image because it's an actual physical failure in the detector.
But here's where the technology gets really clever. The system has a built-in fix. It runs a quality control test, it finds that dead pixel, it logs its exact location on a defect map, and then, this is the cool part, the software just intelligently fills in the blank using data from the pixels right next to it. It basically makes the defect invisible in the final image.
Two other big ones from the detector are shading and ghosting. Shading is just a slow, gradual change in brightness across the image that gets fixed by something called flat field calibration. And ghosting? Well, it's literally the ghost of a previous image that's still lingering on the detector. Each one tells its own unique physics story and has its own specific solution.
All right, let's level up. Now we're getting into some advanced forensics. We're looking at clues that weren't even in the original snapshot of the breast, but were actually introduced while the picture was being taken or while it was being digitally developed.
This slide gives two perfect examples. On the left, you've got acquisition artifacts like grid lines or scatter fog. These happen during the X-ray exposure. Then on the right, you have processing artifacts like ringing, which are created by the software after the picture is already taken. It just goes to show, our detective has to understand the camera, the photographer, and the darkroom.
And here's the crucial pitfall: a processing choice, like using a really aggressive software filter to make the image look sharper, can actually create a brand new false clue, this ringing artifact, or even worse, it can hide a real clue inside its artificial light and shadows.
And of course, as our imaging technology gets more and more advanced, the mysteries just get more complex. The kinds of artifacts a radiologist has to spot are evolving right along with the tech itself. New clues are popping up in 3D mammography or tomosynthesis, and in contrast-enhanced mammography.
So, in 3D mammography, you can get this really specific ripple artifact. It looks like waves spreading out from something super dense, like a little surgical clip. The absolute key to identifying this false clue is knowing which direction it's going.
And here is the detective's secret rule. This is pure physics. The ripple artifact is always perpendicular. So, at a 90-degree angle, to the direction the X-ray tube was moving when it took the scan. This simple rule lets a radiologist immediately spot it, identify it, and dismiss it as a false alarm. Case closed.
Then you have contrast-enhanced mammography, or CESM. Here, artifacts come from a pretty clever trick. taking two different images and digitally subtracting one from the other. But this process has its own challenges. If the patient moves even a tiny bit between the two pictures, you get what's called misregistration, these weird misaligned edges. And sometimes, the subtraction itself isn't perfect, and it creates what we call pseudo-enhancement, a signal that looks like a problem but is really just a mathematical ghost.
Okay, so with all of these potential false clues, from the patient, from the detector, from the processing, from all this new tech, how on earth does a radiologist solve the case every single time? Well, they don't guess. They have a system, a framework.
This is it, the essential troubleshooting checklist. It's just a series of simple questions that act like a process of elimination. Is the thing in the exact same spot on every single image? That's probably the detector. Does it only show up on the processed image but not the original raw data? That's a processing artifact. This logic quickly and reliably gets you to the source of the clue.
And that brings us to the end of our explainer and the end of our entire series on the physics of mammography. We've gone all the way from the photoelectric effect to this, the day-to-day vigilance it takes to make sure all this incredible technology works perfectly for its one true purpose, to find cancer early and save lives.
We started with just part of this quote, but here's the full thing. Because at the end of the day, understanding the story, being able to decipher these clues, and knowing which ones are real and which ones are lies, that is what separates a good picture from a life-saving diagnosis.
Thank you so much for joining us for this entire series. We really hope you found it illuminating.